So welcome to all of you. Now we'll see limit theorems of a sequence. Okay. So first we will see what we mean by a bounded sequence. Okay. So we define a bounded sequence. A sequence xn of a real number n is said to be bounded if there exists a positive real number m, such that mod of xn is less than m for all n belongs to n. That means what? Here what? So every member is less than and greater than some number now. That means what? All the xn, all the sequence, are greater than. So modulus of, so we say modulus is positive now here. Okay. So that means what here? Modulus of every term of the sequence is less than a fixed number m. Okay. All the terms of the sequence is less than m. Then we say that the sequence is bounded. Okay. So that means it is lies between something minus m and m, right? So all the terms are lies between minus n and m. Then it is. That means what? The set is what? Bounded. The set is bounded. So you know that. So the bounded set means what? Okay. So in the first chapter we have seen the bounded set. That means this is the set. The sequence is nothing but a set of the number. So if the set is bounded, then the sequence is bounded. Okay. So now we prove the very important theorem. So always remember that every convergent sequence of, this is very important theorem. Every convergent sequence of a real numbers is bounded. Every convergent sequence of real number is bounded. This we have to prove. Okay. So prove. Let x is equal to xn be a sequence of real number. Let x is equal to xn be convergent and converges to L and converges to L. Okay. So therefore limit n tends to infinity, xn is equal to L. So therefore for given epsilon greater than 0, there exists k belongs to n such that mod of xn minus L is less than epsilon for all n greater equal to k. So I can write this as minus epsilon xn minus L is less than epsilon. Okay. So this is n minus epsilon is less than xn is less than epsilon plus L for all n greater equal to k. Okay. Okay, so instead of this, what we will do? What we have to prove? Mod of xn is less than m. We have to prove that mod of xn is less than m for all n greater equal to k. So we write mod of xn now. I can write this is what? Xn minus L plus L. Okay. Now by triangle inequality, I can write this is what? Xn minus L plus mod n. So that means what here? Xn is less than. So this is epsilon plus mod n for all. This is true for all n greater equal to k. This is true for all n greater equal to k. Choose m is equal to mod of x1, mod of x2, dot. This is true for, see, mod of xn is less than this epsilon plus mod of x. This is up to k. This is not up to k. This will be less than this. But what about the previous one? So that means what? Mod of xn minus xk minus 1. Mod of xk minus 1. And this is what? Epsilon plus mod n. Okay. So then mod of xn is less than m for all n belongs to n. For all n belongs to n. Therefore sequence xn is bounded. Sequence xn is bounded. Now we prove a theorem. Let x is equal to xn and y is equal to yn be sequences of real numbers that converge to x and y respectively. Let C belongs to R, then the sequences x plus y, xy, cx converges to x plus y, xy, and cx respectively. Okay. So prove this one. Prove. Let sequence xn and sequence yn be the convergent sequences and converges to x and y respectively. Okay, we'll do for. So therefore what? Limit n tends to infinity, xn is equal to n, convergence to x. Now this is x, and limit n tends to infinity, yn is equal to y. This is given. Therefore for epsilon greater than 0 there exists k1 k2 belongs to n such that mod of xn minus x is less than epsilon by 2 for all n greater than equal to k1. I call this as 1. Mod of xn minus y less than or equal to epsilon by 2 for all n greater than equal to k2. I will call this as 2. I will take k as maximum of k1, k2. Then both 1 and 2 holds for n greater than equal to k. Okay, so I can replace this k1 and k2 as k now if I take k as the maximum of k1 and k2. So now we want to prove this x plus y is converges to sequence x plus y is convergent to this. Okay, so what I will do, I will write this as mod of xn plus yn minus x plus y. I want to show that this is less than epsilon. Okay, so now this is equal to mod of xn minus x plus yn minus y. So by triangle equality, this is mod of xn minus x plus mod of yn minus y, right? And this is less than epsilon by 2 plus epsilon by 2 for all n greater than equal to k, right? So therefore mod of xn minus xn plus yn minus x plus y is less than epsilon for all n greater than equal to k, right? So therefore limit n tends to infinity xn plus this is yn, xn plus yn is equal to x plus y. So therefore sequence xn plus yn is converges to x plus y. Okay, so the first part is over now. First part is over. Now do for the second one now. For product, we do for the product. So what we have to prove? Xn yn minus xy is less than some epsilon. Okay, that we have to prove. Okay, so I can write this as mod of xn yn plus this is xn y plus xn y minus yn, or plus yn xn yn plus xy minus xy. This is minus xy. Okay, now check whether this is hold. X and y get cancelled. So this is what x and y. Okay, so no problem for this one. I will take xn common from this one. Xn common, y minus y. Y minus y. And I will take y common from this one. So y common, xn minus x now. Okay, so now this is less than or equal to mod of xn yn plus y and mod of y xn minus x now. Okay, so now this is less than mod of xn mod of yn plus y. This is equal to xn plus mod of y mod of xn minus x now. Okay, okay, since I will call this as 3 now. Okay, I will call this since sequence xn is convergent, therefore mod of xn is less than or equal to m for all n greater than equal to k. Okay, for all n, actually not for all n instead of this, for all n now. This is true for all n. Okay, the sequence is bounded. Every convergent sequence is bounded. Okay, so we write this as less than m. This is epsilon by 2 plus mod y into epsilon by 2. Mod y into epsilon by 2. Epsilon by 2. Okay, so therefore what? Mod of xn minus yn, xn into yn minus xy is less than this number. So I can write this is what? I can say this is what? Epsilon dash for all n greater than equal to k. This is true for all n greater than equal to k. Epsilon very small. You may replace this is what? In the definition, what you may write this is what? Epsilon upon 2 instead of this epsilon upon capital M, you can write this epsilon upon twice m. Okay, so because twice you can take this as twice m. So what? Mod y. So mod y you can take this for yn you can take this one epsilon upon 2 times mod y, 2 times mod y. You can take this one because this is also very small. Okay, so you can take this one epsilon dash for us. Therefore limit n tends to infinity xn yn is equal to xy. So therefore sequence xn yn is convergent is convergent sequence and converges to and converge to xy. Okay, so on the same line you can do the third one also for C, which is very easy now. So third one is very easy, you can do yourself. Okay, you can do yourself. Okay, now we'll write a theorem. If x is equal to xn is a convergent sequence of real numbers and if xn is greater than or equal to 0 for all n belongs to n, that means what? The sequence of non-negative terms, then x is equal to limit n tends to infinity, xn is also positive. Limit of a positive sequence is positive. Okay, so this is theorem. So now we'll see the next theorem. This is very important. So this is what? Quiz theorem. Okay, statement. Suppose that x is equal to xn and y is equal to yn. X is equal to xn, y is equal to yn, z is equal to zn are sequences of real numbers such that xn is less than yn is less than zn, xn is less than y is less than zn for all n belongs to n, then and okay, not then, and limit n tends to infinity, xn is equal to limit n tends to infinity zn, then sequence yn, so the sequence is yn is convergent and limit n tends to infinity, xn is equal to limit n tends to infinity yn is equal to limit n tends to infinity zn. Okay, so what we are given, limit n tends to infinity xn and limit n tends to infinity zn, so that we have provided to, that means what? Okay, so we'll prove it. Okay, so prove, given that for sequences xn is x1 is less than or equal to yn is less than or equal to zn and limit n tends to infinity, xn is equal to limit n tends to infinity zn is equal to n, will say this is n say. Okay, so therefore mod of xn minus n is less than epsilon for all n greater than or equal to k, and mod of zn minus n is less than epsilon for all n greater than or equal to You may take this as k, no problem. You may take this k as the same now here. Okay. So what does this implies? This implies that minus epsilon less than mod of xn minus not mod xn minus n less than epsilon, and epsilon less than zn minus l less than epsilon. Okay, so this implies that l minus epsilon xn is l plus epsilon, and l plus l, this is minus l minus epsilon zn is less than l plus epsilon. Okay, so xn is less than yn is less than zn, right? So this implies that now your xn is greater than l minus epsilon. So this is what l minus epsilon x2 is less than yn is less than zn, and your zn is what? Less than l plus epsilon. L plus epsilon. So what does this implies? This implies that l minus epsilon and this l plus epsilon. Okay, so this implies that mod of yn minus l is less than epsilon for all n greater than equal to k. This is true for all n greater than equal to k. This is epsilon. This is epsilon. So therefore limit n tends to infinity, y is also n. Okay, so this implies that sequence yn is convergent. So thus limit n tends to infinity xn is equal to limit n tends to infinity yn is equal to limit n tends to infinity zn. Okay, so that means what? If the extreme has the same limit, then the middle one has also the same limit. That is the Quiz theorem. Okay. Okay, we'll take a problem. Show that sequence twice n plus 1 upon n converges to 2. Okay, solution. xn is equal to twice n plus 1 upon n. Okay, limit n tends to infinity, xn is equal to limit n tends to infinity twice n plus 1 upon n. So this is limit n tends to infinity. I can write this is what? 2 plus 1 upon n. So this is what? 2 plus 0. This is 2. Okay, so therefore sequence twice n plus 1 upon n converges to 2. Show that. Next problem. Show that the sequence sin n upon n is converges to 0. Okay, solution. Xn is equal to sin n upon n. Is it correct? Yes, sin n upon n. Okay. So we know that minus 1 less than or equal to sin n is less than or equal to 1. This is known to you. We'll divide by n. We can divide by n because n is a natural number. Okay. So minus 1 upon n less than or equal to sin n upon n less than or equal to 1 upon n. Okay. So limit n tends to infinity minus 1 upon n, limit n tends to infinity sin n upon n is equal to limit n tends to infinity 1 upon n. So this is 0. Limit n tends to infinity sin n upon n is equal to 0, is less than or equal to 0. Okay, so both the limits are exist. Both the limits are exist. This is your xn, yn, zn. Okay, and limit of xn is same as limit of limit of zn. So then the limit of yn is also exist, and that is what whatever the limit of xn and zn. So that will be your limit of y. So therefore, what limit n tends to infinity, sin n upon n is equal to 0. Therefore, sequence sin n upon n converges to 0. Your converge to 0. Next, show that the sequence xn where xn where xn is equal to 1 upon n plus 1 square plus 1 upon n plus 2 square plus dot 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 plus 1 upon n plus n square. Okay, solution given that xn is equal to 1 upon n plus 1 square, 1 upon n plus 2 square plus dot 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 plus 1 upon n plus n square. Okay, so what we'll do, see, this is what here we can take the addition of this one, because all the denominators are not same here. Your numerators are same, but the denominators are not same. So what we'll do, we'll write this as, we know that, see, 1 upon n plus 1. I can write this in n. This is what 1 upon n plus 1. Okay, I write this as a square. And this is just, I will write this is 1 upon n square. I can write this. This is what 1 upon n plus n square. I increase this denominator. And I decrease this denominator here 1. I decrease this denominator by 1. So what here? So you know that n plus n is less than n plus 1 is less than n now. This relation. So what here? If you have taken the reciprocals, oh, this is opposite now. This is what? Opposite. So n plus n greater than n plus n is greater than n. If you take the reciprocal, you get this one. Or you take the square of this one, no problem for the square of. Inequality remains as it is. If you take the reciprocal, we get this now. Okay. So what we will do now, for each term we can write like this. So we can write this as 1 upon n plus n square plus 1 upon n plus n square plus dot dot dot. How many these are n terms? 1 upon n plus n square. Okay. This is less than equal to. I will write this as xn now. And I will write this as what? 1 upon n square. 1 upon n square plus dot dot 1 upon n square. See, we can write. So these are the n terms. So what denominators are same. So I can write this as n upon n square. Okay, less than xn less than, what is this? N upon n square. Okay, so what is this then? So this is 1 upon twice n square. So this is 4n less than equal to xn less than or equal to 1 upon n. 1 upon n. So write limit n tends to infinity 1 upon 4n. Limit n tends to infinity xn is less than 1 upon limit n tends to infinity 1 upon n. So this is 0. This is less than equal to limit n tends to infinity xn is less than equal to 0. So by F.Y.B.Sc theorem, limit n tends to infinity xn is equal to 0. So here what? Show that the sequence xn where this each converges to 0. This is your problem. So by F.Y.B.Sc theorem, just we have proved this is converges to 0. So therefore sequence xn is converge to 0. is converges to 0. Converge to 0. So we'll take the next problem. We'll take a next theorem actually. Okay. Let the sequence x is equal to xn converges to n, then the sequence mod of xn is also converges to mod n, and the sequence root of xn is also converges to. Okay, so that will do. So for convergence root, for root 1, for if you have to draw a root, you have to take the sequence of the positive terms. So you cannot take here now. Okay, so proof. Okay. Given that sequence x is equal to xn is converges to n. So therefore limit n tends to infinity, xn is equal to n. Okay. So therefore for given epsilon greater than 0, there exists k belongs to n. Such that mod of xn minus n less than for all n greater than equal to k. And what you have to prove? You have to prove that mod of xn is also convergent to this. Okay, so we know that. Just we can say we know that in mathematics. So this is mod of xn minus mod of n. We have proved this one, mod of xn minus n. That we have proved. Okay. Now this is less than epsilon. For all n greater than equal to k. Right. So therefore limit n tends to infinity, xn mod of xn is equal to mod n. Right. So therefore sequence mod of xn is converges to mod n. Okay. So it is proof is over now here. Okay. Similarly the sequence xn is converges to n. Suppose that xn is greater than equal to 0 for all n belongs to n. Then the sequence root of xn is converges to root n. Okay. So this also we can prove like this. Okay. So no need to prove this one. Okay, remember this as. Okay. So up to this is okay. So now we'll stop here and we'll take a next part of the sequence. Okay. So up to this we'll stop here.